So, one of the main reasons for polar coordinates is that you can easily describe some very interesting pictures, polar curves. So here's what the functions look like in polar. Usually, instead of writing y equals f of x, we write r equals f of theta. Almost always for polar functions, we're going to let theta be the input variable and r be the output variable. And that's a little weird because we always write them in the order r comma theta, so it's like we're writing the output first, but just historical. That's how it goes. So theta is the input and r is the output. So here's some examples. The first one is r equals 5. So that's a constant function, and it means it doesn't matter what angle you put in, r is going to be equal 5. There's nowhere to plug in theta. So that means it's a circle. It's a circle of radius 5. For every angle going around that circle, the dot that you draw on the radius will be at the radius 5. 5 away from the center. So that's a circle of radius 5, r equals 5. So we already know how to write a circle. We could write x squared plus y squared equals 25, but it's faster, r equals 5. Here's somewhere that just give you some interesting pictures that you haven't seen before with x and y. Like r equals theta, instead of if you wrote the equation y equals x, then what you get is a diagonal line. When you write r equals theta, you get this interesting nested or overlapping spirals. Starts in the center, for instance, the very, very center point. If you have theta is equal to 0, then the radius is equal to 0. So you get a dot right in the middle. Then as theta goes up to pi over 2, or 90 degrees, so does the radius. The radius has to climb right up to pi over 2. And then when theta gets to pi, or 180 degrees, then the radius has to be equal to pi. So right where it crosses, well, say the dark blue line is the positive radiuses, and when it hits pi, it crosses that pi. Now the orange line is for negative radiuses. So when I let when theta is negative pi, then the radius will be negative pi as well. But that means that we're going to be 180 degrees away from the actual angle negative pi, which points to the left. It'll be 180 degrees away, pointing to the right, so the orange line goes the opposite direction. And then so on. You can go all the way around and around and around forever. Every time it comes back, it's added another pi or another 2 pi. So a more interesting spiral, I don't know, that's pretty interesting, but here's a spiral that I like, is r equals e to the theta. So that's an exponential function like y equals e to the x. But for r equals e to the theta, what you get is a spiral that looks like this. It gets infinitely small in the center, and it gets big really fast as you go out. Because it is exponential growth, so that radius is going to grow really fast as theta increases. But the thing about e to the theta is that it never hits 0, and it never goes negative because it's a e to a number. So it just gets smaller and smaller and smaller. When you put in negative angles, you just get a very, very, very small radius, and it shrinks down very, very small. Let's see. Okay, then here's interesting ones. When you put in trig, like r equals sine theta. So this time I decided to make it a little easier to graph by saying sine theta plus 1, which makes sure that it shifts the graph of sine theta up so that it's all above the axis, or touches the axis, all greater than or equal to 0. So you can draw the graph of r equals sine theta plus 1 on a normal graph, a regular Cartesian graph, where theta is the horizontal and r is the vertical. But if we're talking about polar points, then we'll need to plot it on a polar graph, where r is the radius and theta is the angle. So you can figure out what r equals sine theta plus 1 looks like. It's this upside down heart shape on the right, by first drawing r versus theta on a regular Cartesian graph. And that's the picture of sine theta plus 1. And so, for instance, when theta is equal to 0, that's the first point at the left, then that makes r equal to 1. So when theta is equal to 0, r is equal to 1, which is the point right here. That's theta is equal to 0 and r is equal to 1. Then when, for instance, you get to theta is equal to pi over 2, that will be the high point of the sine graph. So it's right there. Theta is equal to pi over 2. And that means when theta is equal to pi over 2, you get r is equal to 2. So 2 away from the center. And so on. As you keep going around, you can plot points from the theta versus r picture that we see from sine theta plus 1 and put them onto the polar graph, and then eventually get that whole shape. So we'll do some more of those as examples. For now, let me just show you some of the pictures that you can get. Like here's r equals cosine theta plus 1. It's a similar shape, but it's a heart on its side. Here's r equals 1 minus sine theta. I needed to draw a couple of pictures to remember what 1 minus sine theta looks like. You have sine theta, and then negative sine theta flips it around the x-axis, or the theta axis, and then plus 1 shifts it up. So there's the same heart shape. If you multiply the angle inside by a number like cosine 2 theta, you can get multiple petals of a flower shape called a rose. And if you then multiply outside of the sine or cosine, you can get things that have a loop-de-loop inside, and this one is called a limacon. So we'll need to work some more examples more carefully, but just to give you an overview.